I was able to resume the local recording. There it goes. All right. So let's review the background. I forgot to go look up good old Mr. Hook there. I don't know if they call him doctor. Back then, a PhD doctor of philosophy was sort of like the idea was just taking root, and of course the medical doctors who were heathens in their own right, meaning like they didn't understand things. Like they were, oh well, you can't call somebody who studies natural. They called science natural philosophy. That's where the PhD comes from, Doctor of Philosophy. But anyways, Hooke was quite a long time ago. So let's think about it. Hooke's law. Hooke's law describes a spring force. And we talked about three major points. It's position dependent. So we got F equals negative kx, although many times the negative is dropped because everybody sort of knows the negative sign is there, but we want to keep that in mind, and that's where this comes in. It's a restoring force because when we displace it, we have to exert a force to displace it. We have to exert a force to displace it. The spring pulls back. It resists us. The spring resists us. And the more we pull, the more it pulls back. In fact, gravity does change in the case of big distances, but near the Earth's surface, it doesn't. The gravity, if we try to push something upwards, it resists us in a constant amount. So it's not a position-dependent force. And it's also a conservative force. So that way it is like gravity. So what we put in, you get back. So in the case of gravity, I lift something up in the air and then I drop it. And the work I put in to lift it, I get back in kinetic energy of the block. And so if I want to kill the roadrunner or I want to drive a piling into the ground, I can add energy by lifting something, and then I drop it, and then I get it back. So even though we express it as put in, get back, remember it's in the energy formulation. It's all based on energy. So we put energy in, we get energy back, and we get all of it in principle. Everything we put in, we get back. And because of all these three things, these three characteristics, it also means that we have the possibility of oscillations. gravity alone, you don't have the possibility of oscillations unless you set up the ramp. But for a spring, you don't need a ramp. A spring, it will make oscillations for us all by itself. And I'm going to go back over that. I'm going to go back now, and we're going to make a more detailed discussion of the conservative force, and which we did last time, but I have a little bit different way to show it. And then the part about oscillations. And the idea is to understand, especially in the case of the oscillations, where the formulas come from that we use. I have all kinds of notes here. And so, now you can't see it. There we go. So the energy we put in can be returned. So first we have to recall stuff we learned with graphing and speed, and so we have to have a little bit of a digression here, a review digression. So remember that distance equals speed times time. So if we make a graph, and we have time, and we have speed, and in this case we'll say that acceleration equals to 0, that means that the speed is constant. So then if we have a 0 time, and let's say t1, t0, which happens to equal 0. If we want the distance, we'd say d equals v times t. And then we'll say t1. And of course, give me a minute. Yeah, that's good enough for now. Notice that v, which is this distance here, times t1 is the area of this rectangle. And in this case, v is equal to a constant. So now let's take the next step here. So now acceleration is greater than 0. So hopefully you remember then, it's greater than 0, and it's constant also. Acceleration is constant. So now we have some V final, V initial, T initial, and T final. So once again, we say, okay, what's the area of this? Because we know that the distance is going to be the area. So since VI and TI are equal to 0, we just realize it's the area of this triangle, which, well, it's always going to be the area of the triangle. So we know that that's going to be 1/2 the base times the height, which is going to be equal to 1/2 of V final times T final. But we also know that V final equals the acceleration times T final. So at the end of the day, this is 1/2 AT final squared. So that should all be familiar, but I just wanted to make familiar, at least if you don't remember it outright. So then, let's say now we're going to stretch the spring. And so we have this general equation at work. So this is energy formulation. We've talked about this also a little bit. So everything is in joules. So if we do, when we pull on the spring, we do work. And that work is equal to F times the distance. And in our case, this is going to be F of us pulling, or let's just say pulling the spring, times the stretch, and we call that X. So if we can make a graph of this once again, and we go, oh boy, I bet you there's an area something going on again. Now the reason it's positive here is because this is the force we're exerting, not the spring. This is the force that we exert. F final starts at 0. And we see once again we have 1/2 F final times X final. However, F equals Kx. So this equals 1/2 Kx squared. and if you will, it's F, in this case, it's X final. But it turns out that this is true. No matter what is X, that's what it equals. So we stretch a spring to some distance X. We put that much energy into it. We put 1/2 kx squared into it. So if we were to make a graph of energy, because the potential energy, remember, because we're pulling the spring back, so we're adding energy to it. So nothing's moving, so this is potential energy. So a reasonable definition of potential energy, so that's this special equal sign, is energy we put in and because in this case it's equal to 1/2 kx squared, and if this is x, we should remember that this is x squared is the equation for what's called a parabola. And what it means is that ultimately, nice symmetry there, huh? Wonder if I can, no. Oh, wait a minute. I might be able to move this over a little bit. There we go. Love computers. So whether we stretch or compress, if we stretch or compress, the PE increases. So if we stretch it out to here, and I don't know, I'll just call it x1 in case I want to do another one. At this point, there's a PE equal to 1/2 kx squared. And since I haven't let it go yet, the KE equals to 0. And because there's no friction, that means that that means that energy mechanical equals a constant, which equals PE plus KE so when PE equals 0, this means that this means, let me redo that. It's the equal with the greater than. This implies that KE equals to the PE max, or the PE start. So at the bottom here, PE equals 0 because X equals 0. And the KE equals 1/2 K x1 squared, which also equals 1/2 mv squared. So if we know K and we know the mass, we can predict the speed. Or we could measure the speed and we could predict how high it goes. This is what you did in the ballistic pendulum. So this is why we call the spring force a conservative force. Mathematically, any conservative force is a force that you can create a potential energy equation. So if you can create a potential energy equation, then it's a conservative force. Yeah, Ghazal, I think I addressed that, right? Always negative kx. The distinction here is that I said that this is the force I exert, so it's positive in this case. So when I stretch the spring, for me, it's a positive force. The spring is negative because it opposes me, and that's why it's called a restoring force. Yes, and that's right. That's why I said the reason this graph is positive is because this is f of us. But for f of the spring, it's negative. You're welcome. No, it's important. That's why I get pissed off when textbooks aren't careful with the negative sign. And they don't explain why they're putting it or not putting it. I gotta stop writing them. Gotta go back to black ink for the when I write out these equations. It looks prettier. Now, the oscillations are because the PE graph, and if you will, the equation, is symmetric. And also because we have the possibility It's because, okay, first of all, two things. First of all, X can be B. I already said the word B. I already wrote B. Can be positive or negative. And the potential energy graph is symmetric, which means it's the same, or it's mirror for positive X and negative X. Right? I mean, that's just a fancy way of saying if I take a marble and I put it in a bowl and I put it up on the side of the bowl, if I let it go, it's going to go back and forth. But that's gravity. And gravity, to do that, requires us to build a physical ramp. The spring doesn't require that. And now this is pretty straightforward. I wrestle with how deep to go with you guys, but sine waves and cosine waves are everywhere, not just simply in radio waves, but in physical things. You see them. You see things oscillating all the time. Scary things like, remember the July 4th earthquake? I was on the beach, and it was weird because it was like being on a bowl of Jello. And then at the next day, was it the next day? I was on my back porch reading a book, and then I felt the earth starting to move. It was the aftershock was pretty bad, and the telephone poles started waving. And because there was a what we call a resonance, they started really waving. It was really I was like just mesmerized because I knew I could see them start swinging more and more because there is in resonance. I'll talk about that a little later if you like. And I thought these telephone poles are going to snap off. And the scientist in me is fascinated. But my reptilian hindbrain is trying to tell me to get up and run, you stupid shithead. But it stopped all of a sudden, but it was pretty frightening. Okay, so let's get into the equations of oscillation. Because this will help us to understand the analysis. So we say F now of the spring is negative Kx. And there's also a thing called Newton's second law, which says that we can multiply the mass times whatever acceleration we see, and that will equal the force. And basically, the way you do that, it means that if I want, usually the way it's stated is if I want to accelerate something at a certain number of meters per second squared, then, and it weighs, and it has a certain mass, I have to exert that much force to make it accelerate that much. So we can rearrange this equation, mass times the acceleration plus kx equals to 0. So I just moved the kx over to here. So then we can do another rearrangement. We're going to say a plus, we're going to divide by m times x equal to 0. So now we have to do another review. Remember that speed equals delta x over delta t, and that acceleration equals delta v over delta t, which also equals delta x over delta t, or it equals delta x divided by delta t squared. And remember, the deltas mean the change. So in calculus, we just say that we use a different notation because we call this the derivative of x with respect to t. And again, that's just when something isn't you can't always use delta x, because if x is not constant, or if you have an equation for x, that's all that means. No big deal. Another way to express it is like this, with a dot. The first time derivative. And a equals dv dt, which can be v dot. Dot just means time derivative. I think I said that already, right? And then it also means that we're taking the second derivative of dx dt. So we also say the acceleration is x dot, double dot, excuse me. Sorry? X double dot, remember the first time derivative of x is x dot, so or up here, delta x, delta t. And when I take the time derivative again, because remember, acceleration is the time change in velocity and speed, so this could also be expressed at d squared x dt squared, but this x double dot is acceleration. The second time I hit it with the time change. So I hit it with the time change once, I get x dot. I hit it with the time change twice, I get x double dot. Is it making any sense? Okay, good. I'm glad I could do that. I know it's a little scary, but at the end of the day, you don't actually have to understand what derivatives are. I mean, when I first learned them, I was just told that this is, I was given a recipe, that's all. And eventually you kind of like, it kind of sinks in over the years, but you can do calculus with just recipes. I did it for years. So notice then what happens here. This becomes x double dot plus k over m x equals 0. And it turns out that x, when you get used to this sort of thing, you right away say, oh, x is actually going to be a sine of x. Because look at it. I'm saying that if I take the distance and multiply it by k over m, it's going to equal to the acceleration. And it's like, what? How can that be possible? Well, it can only be possible if we use something that repeats, and a sine repeats, right? See, that is where the oscillation comes in. Because sine is a repeating. That's called an oscillation. And I finally found this great, let's see if I have it queued up. I think I do. I do. I added it to the playlist. This is pretty darn cool. Oh, hold on. I don't think I have to set it up so you can hear the sound. Yeah, here it is. Of course, he has a lab coat. And that's something that sine waves are everywhere. Mother Nature is just amazing. So that shows you as a demonstration that it is perfectly fine to use a sine wave to describe the spring's behavior. So let's do a little bit of algebra, well, calculus now here. Now it's going to be trippy. That might be a little scary, but it's really not that bad. Let's copy this. So we need to just add something. We're going to add a constant, sine of cx. So the first time derivative, x dot, is going to equal to cosine of cx plus I have to take the time derivative in here. And so that is just C. Because X itself doesn't have a time. Now, this is a little confusing the way I'm doing this. Maybe I better do another. Hold on, back off on this a minute. Let's just, I have my notes are different. Let's do my notes. We need to, so let's say we're going to let's call this, and now it might start to look familiar, omega t. And then you're going to say, what? Okay, so X is going to become theta, angle. Distance, speed is going to become omega. So this is radians. Remember, if you have an angle, theta, we got 0 radians, pi over 4 radians, right? Pi over 2, pi, etc. Omega is radians per second. And also alpha is A. A is alpha, radians per second squared. So then that is theta, theta dot, and theta double dot. Well, theta is theta, this is omega, this is alpha. So in this case, I have omega is equal to a constant. So there's, omega is equal to a constant. And if at any given time, just like in the graph we just saw, and this is the sine of omega t, and any time I just multiply omega times t, and then I know what the angle is, then I can plot sine. Is that blowing anybody out of the water? Should I try that again? Okay. Good. I'm sorry for the stopping and restarting. I should have just had faith in my own notes. So, x dot is going to be cosine omega t, but I have to take the time derivative in here, and since omega is a constant and there's a t here, so that's just omega. And then x double dot is I take the derivative of cosine, which becomes negative sine, and then I have to take the derivative again inside, but it's just the same thing. So now it's omega squared. Now again, guys, you don't have to understand this 100%. I'm just showing it to you so you understand where the ultimate equations come from. So now let's plug it in. We have minus omega squared sine omega t plus k over m times sine omega t equals 0. And for this to be true, omega squared has to equal k over m. So omega equals square root of k over m. That's all there is to it. I remember learning this. It took me years to put this all together in my head when they taught this to me. It was so stupid. If somebody had just written out what I just wrote out from the beginning, I would have understood it so much more easily. So we also have, remember we talked about frequency equals cycles per second. Period is 1 over frequency equals seconds per cycle. And when it comes to a sine wave, if I plot this, remember time, but then theta equals omega t, theta here equals 2 pi. So omega is radians per second. So in this case, period t equals seconds per 2 pi. So that allows us to see, give me a minute. All right, which is 1 cycle. Oh boy, come on, Harry. I should have written this one out better. I know that omega equals two pi f. Right, okay. So we get cycles per second times 2 pi. Then that equals radians. Nope. Sorry, that's wrong. It is sort of right, but because there's 2 pi radian, that's it, now I remember. 2 pi radians in 1 circle, once around, per cycle. Yep. That's what I want, per cycle. Yeah. And that's how we end up with the number of radians per second and number of radians, 2 pi. Gosh, I'm sorry I'm screwing this up. How am I? Oh, yeah, 2 pi 1. Oh, sorry, I'm not doing this right, but I think you follow along with me. So then t equals to 1 over f. Ah, right, that's what I wanted. So we got f equals to omega over 2 pi equals 1 over omega over 2 pi. So that equals 2 pi over omega. And also omega equals square root of k over m. So this equals m over k 2 pi. Yeah, so that is, yeah, equation 4. So all that just so I can get to equation 4. I thought I hit upon a new way to explain it down here. And it kind of went down in flames. So the idea is just, we'll just call this a definition instead of me trying to derive it. Okay. Does anybody need me to back up to probably the previous slide? I think I may have pulled it out away from you too fast. Yeah, should have just stuck with your notes, Harry.